E is in the most general case I omega G of R prime J R prime, right? This is the fact. And then I can rewrite this as I omega mu I plus del del over K naught squared. I think this is in chapter 1 of my book. Scalar Greek function. The R prime. Right? And then in the far field, all these waves become spherical waves. All of them become spherical waves in the far field. Spherical waves behave like plane waves. Because they behave like plane waves, in the far field you can replace the del operator with ik, with a minus k over k naught squared. And then the g can be, is this function over here. And then in the far field, you can approximate this with something simple. Aditya, do you remember how you can approximate that? R prime is the source location J. R is very far away, the observation point over here. So R is much, much larger than R prime in the far field. Then R minus R prime magnitude can be approximated, right? And then, so this can be approximated as e to the ikr over 4 pi r e to the minus I k dot r prime. Understand? You learned that in your undergraduate case. And you can go to that approximation and get this. And then finally, what you have is that this is equal to, I can replace this with unit vectors. And then I can replace this with the spherical wave outside. Okay, I'm actually running out of time. So this is the Fourier transform integral. This is the Fourier transform integral. So the far field is always the Fourier transform of the sources you have induced on the scatterer. So if you send X-ray to a crystal lattice, the X-ray scatters of the atoms in the crystal lattice. Those atoms have sources, and in the far field you get the Fourier transform of the crystal lattice, which is another crystal lattice. Okay. Let me go back to this. So approximation theory says this, which means that if f of omega is band limited, it will look something like this. And then you convolve with the impulse train. These impulse trains are actually, if they are spaced close apart, this impulse train will be spaced further apart. Which means that if you have high sampling rate, this impulse train in the Fourier space will be further apart. So if you convolve with this thing, then what you have is a whole bunch of things. Like this, right? You convolve this, you get that. And if there's no overlap between these functions, if you window it, you just window one of them, you get very good replica of the original function. Okay? But when is it that there's very little overlap between them? When this is band limited. If this is band limited, you can show that this tail is exponentially small. Okay, this tail will be exponentially small. So the errors that you make is due to those overlaps. And those overlaps are exponentially small. So if this function is band limited, you have exponentially small tails on the outside. Aliasing gives rise to only exponentially small error, which means that you can go from here to here, incurring exponentially small errors. So this is just an example of approximation theory, where things can be replaced with a finite set of numbers, and yet the error is exponentially small. Let me see, I don't have much time now. So this is actually converting an infinite dimensional matrix system, vector system, into a finite dimensional vector system. I will call this the subspace projection method. So it's very similar in theory to the fact that if I have a very large matrix system, and this is say a billion by a billion, 10 to the 9 by 10 to the 9, and this system is very hard to solve on the computer, right? Then somebody clever comes along, a very clever graduate student comes along. Say, I want to find ways to reduce this metric system to be something smaller. So why don't I do this? This is maybe 100, okay, instead of a billion. But this is still a billion by 1. So this is still a billion by 1. I substitute that into the above. Okay, I get a new system, a dot xn an is equal to b. This is still a billion by 1. Okay, and then the next thing I do is to test this equation with another vector which is also very large. So a billion by 1 still. And then if I do that, then I have a new system. This is n. An is equal to, say, Pm, right? Then I have a new system. And this is 100 by 100. And this system is a lot smaller. So this is essentially the essence of this method, a subspace projection method, where I find subspaces to approximate the original space. And then I end up with solving a much smaller system. Okay? So the key is on how to find this approximate subspaces. Okay, approximate subspaces to be a good approximation of the original space. So if you're clever, you can find these subspaces. You can define all kinds of basis functions that are clever replica of the original space. Yet you can get exponentially small error, as we can show in signal processing. If you're clever, you can find approximation theory that actually almost replicate the original function within exponentially small error. And then you can do computation. We only have finite resource to do computing, even though we have a petascale. Why is it now petascale computer? It's still finite, right? You can use all the resources you have. Probably would be very difficult for them to solve a billion by billion matrix system. So finite element method of moments, Galeckin's method can all be cast into this framework. It's a subspace projecting method. You find a smaller subspace to solve that problem. You can do that for integral equation operator. You can do that for differential equation operator. It actually is the same spirit. It has the same spirit. Okay, any questions? If not, then we resume next week again at 9 a.m.